So now we're going to take a look at calculating values and other bases. This is probably the most complex topic in Chapter 5, so it's going to be really valuable to watch this video more than one time. So in a non-base 10 system, you're using powers of different numbers. In base 10, you're using powers of 10. So for instance, the ones place is the number of ones you have times 10 to the 0. The number of tens you have is the number of tens you have times 10. The number of hundreds is the number of hundreds times 10 to the power of 2. So that's what we mean by when we're saying powers of. In base 10, we would use the digits from 0 to 9. Just like if we were in base 5, we would use 0 to 4. So notice whatever your base is, the numerals end 1 prior to that. At 5, you kind of have to recycle this, and you can't write a 5, so you have to write 10 base 5. So if I was to follow this pattern out, I would have 1, 2, 3, 4. I hit base 5, so I'm going to have 10 written in base 5, 11, 12, 13, 14, 20, base 5, and it's going to keep on repeating in that way as we move through powers of 5. Likewise, if I was in base 8, I would use digits 0 to 7, so I can't write the number 8. The counting pattern would be 1 through 7 would be normal, but then what was formerly 8 becomes a 10. And what was formerly 18 becomes 17 to the power, the base 8. And then instead of going to 18, I jump straight to 20. And then instead of going from 79, I have to jump over 80. And that's how I wind up at 100. So these different values basically truncate the number system. If I was in base 16, everything would be kosher up until 16. What is different though is we don't have a symbol for 10, 11, 12. In base 16, your 10 occurs at the number 16. Your 20 occurs at the number 32 because 16 times 2 is 32. And so on. So it's really key that you recognize what we can and can't utilize when we're operating in different bases. If I'm in base 2, follows the same pattern. I can only use zeros and ones. What was formerly 2 becomes the tens place where we add a tens place value. 4 becomes the hundreds, and so on. So in order to work on converting this over, if I have the number 4,302 in base 5, I would take it and I would take each place value and multiply it by the power of 5. So 2 would be times 5 to the 0 power, 0 would be times 5 to the 1, 3 would be 5 squared, and 4 would be 5 cubed. So in base 10, this is 10 cubed, 10 squared, 10, and 1. In base 5, I'm just changing that number out. So our place value is still a power of 5. If I wanted to work and rewrite 384 as a base 10 numeral, I'm going to divide 384 to be able to get those largest powers of the unit. So if I take 384 and I divide it by 5, I get 75 with 4 units rolled over. Now I'm going to take and do 76 divided by 5, which would be the equivalent of dividing the original number by 25. So basically you want to think, what is the largest power of 5 that you could divide by here? Well, it's probably going to be 5 cubed. So if I do 384 divided by 125, that's actually going to replace all of this as a faster manner to convert between the bases. If I just didn't know the powers of 5 and I just kept blindly dividing by 5, I could still get there by understanding that when I do that division, those numbers are going to correspond to increasingly large place values. So the first time you divide, that's your ones place. Second time you divide is your tens. Third time you divide is your hundreds, which would be 5 squared here, 25s. And then you would keep moving down the line there. Now, addition in base 5 is interesting. I can add together numbers, but when I get something that is 5 or larger, I have to adjust things. So 2 plus 3 is 5, which means I have to put a 0 and carry the 1. Because 5 is like 10, and that's why we're putting a 0 and carry the 1. Because the new 10 is 5. And then I'm going to move on from there. 4 plus 2 is 4, 5, 6, and 7. 7 corresponds to 2. And then I'm going to carry that extra 1. And then last, I'm going to do 3 plus 2 is 5. But I have that 1 carried. So 5, remember 5 goes back to the 0 place. But I have a 1 here, so that's 1 left. And then I have that carrying of the 1. Because I had 1 plus 3 plus 2. Now if I want to subtract, that can be a little harder to regroup. So 4 minus 3, that's easy. That's 1. And 1 is a new number we can have. But 2 minus 4 is a problem because I can't do 2 minus 4. So I have to bring a 10 over and make it 12 minus 4 because we're borrowing. And then that gives me 12 base 5 or decimal 7 fives. So when I subtract, I get 3 fives, which is what happens there. And then 3 minus 1 is 2. So the only problem you're going to run into in subtraction is when you have to basically borrow, because borrowing looks very different in this base. Here's 2 further examples where you multiply. So again, anything 5 or higher, you have to convert into the ones, the tens, the hundreds place, but with powers of 5. And the same thing is true for this multiplication. Everything else procedurally is the same. It's just working with those exact numbers. If I want to divide, it's the same constraint that I had before, that I can't write the number 5 or anything higher. So I'm going to use powers of 5 to find the best answers so that I can do my division. So from that list with the powers, I see that 23 base 5 is going to be the best value to actually divide by. And then I'm going to do the subtraction, and then I'm going to bring that down so I can carry it down and find the remainders, and I'm going to complete the division utilizing that method. The last example we're going to have would be converting from binary to other decimal systems, which can be kind of tricky because there's no spacing here to help us group things out and identify where the number stops and starts. So in binary, I have 1, which corresponds to 1. 0, 1, 1 would correspond to 3. 0, 0, 1 would correspond to 1. And I'm getting this from the chart in the bottom of the window that would be very helpful for you to print out or copy down as you complete this assignment. And then once I take those little bytes and I arrange them into groups that I think are the formations of their numbers, then I'm able to come up with our answer of B35E. And if you remember, hexadecimal does use letters, and so going back to this video to look at those letters is really helpful.